In part 2 of our series on Lewis structures, we're going to review how to draw the Lewis structures that represent covalent compounds and use the concept of electronegativity to determine when covalent compounds form instead of ionic compounds. Now, the general shortcut that we can use, albeit a less specific one, is that covalent compounds occur when the electronegativity difference between the two atoms that are bonded together is less than approximately 1.7. Now, at this point, one of the elements in the bond does not have a high enough electronegativity in order to get the electron to transfer from one element to the other, and consequently the two elements share electrons rather than being held together by opposite full charges, as are the case in ionic bonds. But once again, we will examine the more specific way to do this comparison by looking at electronegativity difference and average electronegativity for a few sample compounds. So, if you remember the procedure for drawing ionic Lewis structures, the covalent process begins much the same, where we need to draw the Lewis structures of the atoms that make up the compound, and in doing so count the number of valence electrons that each element brings, followed by which we need to find what the central atom of our compound is going to be, which is pretty much always going to be the atom with the most unpaired valence electrons, that being the most singular electrons that are not already in a lone pair. So if we do that for the first two, we'll save the two below till the end. Let's take a look at water and carbon dioxide. So hydrogen, as we know, only has one unpaired valence electron, which is why it is often grouped with the alkali metals, even though hydrogen is not a metal. And then oxygen has a total of 6 valence electrons, so we can calculate the total because hydrogen has 1, and we have 2 hydrogens, which brings our total to 2 plus the 6 from oxygen, meaning that we will be looking at a total of 8 valence electrons when we draw the Lewis structure. We can see that oxygen has 2 unpaired electrons, whereas hydrogen only has 1, and therefore we can put oxygen in the middle with the 2 hydrogens surrounding it like this. Likewise, with carbon dioxide, we know the Lewis structure of oxygen already. It brings with it 6 valence electrons, and because we have 2 oxygens in carbon dioxide, we can multiply this by 2 for a total of 12 electrons from 2 oxygens. And then we remember the Lewis structure for carbon has 4 unpaired electrons like this, and again, carbon is one of the few elements that can naturally make 4 bonds, and the fact that it has 4 unpaired electrons explains why. This also shows that carbon is going to be our central atom because it has more unpaired electrons than oxygen, so we can put the 2 oxygens off to the side like this. Now, technically, even before you get to this point, it's good practice to actually confirm that carbon dioxide and water are going to have covalent and not ionic bonds. So let's go and measure the electronegativity values for each element. So carbon's is 2.2, or hydrogen's rather is 2.2, carbon is 2.6, and oxygen is 3.4. So we can do a quick difference of electronegativity calculation. 3.4 minus 2.2 comes to an even 1.2, and then if we do our average electronegativity calculation, 3.4 plus 1.2 comes to a total of 4.6, and if we take 4.6 divided by 2, this we can do quite easily because 6 divided by 2 is 3, and 4 divided by 2 is 2. So our average comes to 2.3, and if we repeat this for carbon dioxide, our electronegativity difference is 3.4 from oxygen, 2.6 from carbon, which comes to 0.8. And then if we do our average electronegativity calculation, 3.4 plus 2.6, a little quick bit of mental math, comes to exactly 6.0, and 6.0 divided by 2 comes to exactly 3.0, so we can go to the triangle of bonding and use this information here. So if we start with water, water's difference in electronegativity would be about here, 1.2, and I believe, let's remind ourselves, average electronegativity of 2.3. So if we check that, we can see 1.2 and 2.3. The intersection is about at this point, which falls under the polar covalent range. And then if we repeat this for carbon dioxide, 0.8 is the difference, 3.0 is the average. So 0.8 falls about here, 3.0 as the average makes this much closer to a true covalent bond or a truly equal electron sharing, but kind of at the intersection between the two. Either way, we can see both elements clearly form covalent and not ionic bonds. So here is where the distinction between covalent and ionic Lewis structures diverges. So because electrons are shared, we need to draw bonds between each of the atoms, and these are what we call single bonds because they represent a single pair of electrons that are shared. So in this case, this is a single bond that represents the sharing of electrons between oxygen and hydrogen, and then we can do that again here. Likewise, we're going to do the same thing with carbon and the oxygens in carbon dioxide here, and here we've added in single bonds. Now, the fourth step that we need is to add back in all of the lone pair electrons that may have been on atoms before they formed compounds. So in this case, hydrogen and carbon do not have any lone pairs, but oxygen does. So what we're going to do, because oxygen has two lone pairs that we can see in its atomic structure, we're going to put those two lone pairs back on each of the oxygens in these structures here. And what we can do, we have the starting total of electrons here. We can count the total number of electrons that we've added. So there are 2 electrons per bond, and we added 2 bonds is a total of 4, plus the 2 pairs of lone pair electrons here is another 4, which brings our total in water to 0 electrons remaining. In other words, we have added in all 8 of the valence electrons between hydrogen and oxygen in order to come up with this structure. To check further that we have the correct structure, all we need to do is count and see whether oxygen and hydrogen have full valence shells. So remember that these 2 bonds indicate the sharing of electrons between oxygen and hydrogen. So this would be 2 for hydrogen, which is full for hydrogen because it only has 1 shell, and 2, 4, 6, 8 for oxygen, which means that we are good. And in the case where we only have single bonds, our structure would be done. However, if we count the total with carbon dioxide, so it started with 12, subtract 2 per bond is 4, which brings us down, sorry, not 12, there were 16 in total because I forgot to add the 4 electrons from carbon. So 16 minus 4 means that we have 12 left. 2, 4, 6, 8 from the lone pairs. So this means we have 4 electrons unaccounted for. Now, if we have electrons unaccounted for after adding single bonds and lone pairs, we can add in what are called double bonds. And a double bond is simply 2 single bonds that connect 2 atoms together. And if we represent a single bond with 1 line, then we would represent, I swear I can spell, we would represent a double bond or double bonds with 2 lines like this. And because I added in 2 bonds, that was a total of 4 electrons, which means that we have successfully used all of the electrons that were available to us from 1 carbon and 2 oxygens. And if we count to see our valence shells are full, 2, 4, 6, 8, 2, 4, 6, 8 for carbon, 2, 4, 6, 8, so we are indeed good. Which brings us to hydrogen cyanide. Now, this is a rather weird compound because it actually has 3 different elements. So what we can do here is repeat exactly the same steps. All that we need to do is draw out the Lewis structures for each of our elements. Hydrogen has 1 valence electron, carbon brings with it 4, and nitrogen, which is 1 element to the right of carbon, would have 5, meaning that our electron total comes to 10. Now, we can see that carbon has more unpaired electrons than either hydrogen or nitrogen, so we would put carbon in the center with nitrogen and hydrogen off to the side like this. Next, we connect each of the elements with single bonds, like so. So if we're keeping track of our electron total, we just added in 4 electrons, 2 electrons per bond, which means that we have 6 left over. Now, adding in lone pairs is relatively simple because carbon and hydrogen have none, but nitrogen has 2, which we'll put back there, which means that we have 4 electrons remaining. Okay, well, if we did what we did with carbon dioxide, we can put another double bond between carbon and nitrogen, but we can see that we still have 2 electrons left over. Well, if leftover electrons are used to turn single bonds into double bonds, if we still have unused electrons, we can add in what's called a triple bond. So if 2 lines is a double bond, then 3 lines will represent a triple bond, which shows that there are 3 single bonds linking 2 atoms together, and we can do that between carbon and nitrogen like this. And that means that we have now exhausted all of our available electrons. And finally, if we count valence shell electrons to make sure that all of our atoms are complete, hydrogen has the 2 from this bond, so it's good. Carbon has 1, 2, 3, 4 bonds for a total of 8 electrons, so it's good. And nitrogen has 2 from its lone pair plus 6 from its 3 bonds is 8. So all of our elements have full valence shells, and we now have a complete structure. Before you move on to the final video in the Lewis structure series, take a look at the last example, CH2S, as well as the practice problems below, as most people find drawing covalent Lewis structures is a little bit trickier than ionic compounds because of the fact that we can not just make single, but also double and triple bonds as well.